Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to continue our lecture on waves and sound, and we've made it to the second objective. Sound is a longitudinal wave, meaning that it is transmitted through the oscillation of particles in the same direction as the wave's propagation. As a mechanical wave, sound requires a deformable medium such as air or water to travel through. These oscillating particles, they compress and expand, creating alternating regions of high pressure, called compressions, and low pressure, known as rarefactions, which carry the sound wave forward. Now, the speed at which sound propagates through a medium depends on two key properties: the bulk modulus and the density of the medium. The bulk modulus measures the medium's resistance to compression, so how easily it can be deformed when pressure is applied. The greater the bulk modulus, the faster the sound wave travels through the material. On the other hand, density refers to the mass per unit volume of the medium. A higher density tends to slow down sound waves because the particles are more tightly packed and harder to move. The relationship between these properties and the speed of sound is expressed mathematically by the formula you see here. This formula says that the speed of sound is equal to the square root of the bulk modulus divided by the density of the medium. This equation shows that sound travels faster in a media with a higher bulk modulus value and slower in denser or less compressible media. To reiterate, sound is produced by the mechanical disturbance of particles in a material along the wave's direction of propagation. For example, when a speaker vibrates, it causes air particles to oscillate, and this creates compressions and rarefactions that travel outward from the source. These waves eventually reach our ears, where they are perceived as sound. Our perception of the frequency of sound is called pitch. Lower frequency sound waves result in lower pitched sounds, like the deep tones of a bass guitar. Higher frequency waves produce higher pitched sounds, such as the notes from a violin. Now, human hearing, it generally ranges from 20 Hz to 20,000 Hz. Sound waves with frequencies below 20 Hz are called infrasonic waves. They're too low for humans to detect. And frequencies above 20,000 Hz are referred to as ultrasonic waves. And actually, ultrasonic waves have many practical applications, including in medical imaging. Now, with that, we can say that sound waves are not only shaped by the medium they travel through, but they're also influenced by the motion of both the source and the observer. And this leads us to the Doppler effect. The Doppler effect is a phenomenon that describes how the frequency of a wave changes when there's a relative motion between the wave's source and its observer. The Doppler effect explains the difference between the actual frequency of a sound and the frequency that's perceived by an observer, depending on whether the source and the observer are moving closer together or further apart. When the source of the sound and the observer move towards each other, then the perceived frequency increases, resulting in a higher pitched sound. On the other hand, when the source and the observer move away from each other, then the perceived frequency decreases, leading to a lower pitched sound. And the Doppler effect helps explain everyday experiences like the changing pitch of a siren as an ambulance approaches and then drives away. Mathematically, the Doppler effect is described by this equation here. F prime is the perceived frequency, This is equal to f, which is the actual frequency of the sound, multiplied by this ratio here. In this ratio, v is the speed of sound in the medium, vd is the speed of the observer, and vs is the speed of the source. Now, what's really important to understand about this equation is the sign convention in the numerator and in the denominator. Let's start by talking about the sign convention in the numerator. We are going to add these two terms together when the observer moves toward the source. And we are going to subtract these two terms when the observer moves away from the source. What about the denominator? We are going to sum these two terms in the denominator when the source moves away from the observer, and we're going to subtract these two terms when the source moves toward the observer. This is really important to understand. Commit the sign convention to memory. One more thing I want to make mention about the Doppler effect before we jump into a practice problem is that this effect is not limited to sound waves. It also applies to electromagnetic waves, such as light, where it causes redshift when objects move away from the observer, and blue shift when they move closer. With that, let's jump into this problem. This problem says a train traveling south 216 kilometers per hour is sounding its whistle while passing by a stationary observer. The whistle emits sound at a frequency of 1400 hertz. What is the frequency heard by the stationary observer when the train is moving towards the observer and when the train has passed the observer? Note that the speed of sound in air is approximately 340 meters per second. To start, we want to write our equation for the Doppler effect. From here, we can begin to figure out what this problem is telling us. It is giving us the actual emitted frequency for the train whistle. That's equal to 1400 hertz. Further, we're given the speed of sound in the medium being air, and that is equal to 340 meters per second. This problem is also telling us that the train is passing by a stationary observer, which means that the speed of the observer is equal to 0 meters per second. This is really important because if the speed of the observer is equal to 0 meters per second, we no longer have this term in the numerator since it is equal to 0. Last, we're given the speed of the source as well. This is equal to 216 kilometers per hour. Our goal for this problem is to solve for two things. We want to solve for the perceived frequency when the train is moving towards the observer, and the perceived frequency when the train moves away from the observer. For that first scenario, train moving towards observer, we are going to have to subtract the two terms in the denominator. So that is our sign convention for that scenario. And for the second scenario where the train is moving away from the observer, the sign in the denominator changes. We're going to be adding those two terms together. Now, before we go ahead and start to plug things in, we need to do one more thing, and that is to make sure that our units are the same for speed. The speed of sound in air is in units of meters per second, and then the speed of our source is in units of kilometers per hour. We want to have the same units for both of those values, so I'm going to go ahead and convert 216 kilometers per hour to units of meters per second. To do that, I'm going to have to apply two conversions. First, I'm going to convert our hour unit to seconds. In 1 hour, there is 3,600 seconds, and that gets rid of hours. And then the second conversion is converting kilometers to meters, keeping in mind that 1 kilometer is equal to 1,000 meters. Now our kilometer units cancel out, and we're going to get our final answer in meters per second. This is going to give us 60 meters per second. Now we can solve the problem, starting with scenario 1. The train is moving towards the observer. For that, we are going to set up our equation. This is going to be F, our actual frequency for the train whistle, multiplied by the speed of sound in air, divided by the speed of sound in air minus the speed of our source. So this is going to be equal to 1400 hertz multiplied by 340 meters per second divided by 340 meters per second minus 60 meters per second. This is going to simplify to 1400 hertz multiplied by 340 meters per second divided by 280 meters per second. Our units of meter per second cancel out. Now for this number right here, the zeros, we can cancel out the zeros. Now we have 34 over 28. Both of those numbers are divisible by 2, so we can simplify it a little bit further and write 17 over 14. And of course, that's multiplied by 1400 hertz. Now what you notice is the denominator 14 and 1400 are both divisible by 14. So if we divide this by 14, we get 1 over here. And if we divide this by 14, we get 100. And then what we have is 100 multiplied by 17, and that gives us 1,700 hertz. Our perceived frequency when the train is moving towards the stationary observer is 1,700 hertz. Let's solve for the second scenario when the train is moving away from the observer. Now our equation looks something like this, where our denominator is the sum of those two terms. This is going to be equal to 1400 hertz multiplied by 340 meters per second divided by 340 plus 60 meters per second. This gives us 1400 hertz multiplied by 340 meters per second over 400 meters per second. We get rid of these meters per second units. They cancel out. Both of these terms have a 0 at the end. We can cancel out. Now we have 34 over 40. Both of those terms are divisible by 2, so we can simplify it to 17 over 20, and that is multiplied by 1400 hertz. Now 20 and 1400 are both divisible by 20, so if we divide this by 20, we get 70. And then what we have left is 70 multiplied by 17, which gets us 1,190 hertz. When the train is moving away from the observer, the perceived frequency is equal to 1,190 hertz. And with that, we've solved this problem, and we can move into our next topic. In addition to changes in frequency due to motion, sound waves can also be affected by objects traveling at extremely high speeds. And this brings us to the phenomenon of shock waves. A shock wave forms when an object moves through a medium, such as air, at or above the speed of sound. When this happens, the object compresses the air in front of it, creating a highly condensed wavefront with a large pressure differential. This sudden change in pressure can create a significant physical disturbance, and it is experienced as a sonic boom. And this is when the shock wave reaches an observer. It's experienced as a sonic boom. Sonic booms occur because the compressed sound waves travel together in a single front, releasing energy in a burst rather than gradually dispersing it over time. Another important aspect of sound waves is how we perceive their loudness or volume, which is directly related to the wave's intensity. Intensity refers to the average rate of energy transfer per unit area across a surface perpendicular to the direction of the wave's propagation. In other words, intensity measures how much energy the wave carries through a given area over a certain amount of time, and that's mathematically expressed in this expression. Intensity, I, is equal to P, which is the power carried by the wave, divided by A, which is the area over which the energy is spread. The units of intensity are watts per meter squared. The intensity of a sound wave really influences how loud the sound appears to an observer. Louder sounds have higher intensities because more energy is transferred per unit area. In addition to being measured by the energy it transfers, the intensity of a sound wave depends on several other factors as well. The intensity of a sound is proportional to the square of its amplitude, meaning that if the amplitude doubles, the intensity increases by a factor of 4. In addition, intensity is inversely proportional to the square of the distance from the source. This relationship reflects how sound spreads out over a larger area as it moves away from the source. And as it moves away from the source, its energy becomes less concentrated. This is why sounds become quieter the further you are from the source. Now, sound intensity is measured in decibels, which is a logarithmic unit that accounts for the vast range of sound intensities that the human ear can detect. The decibel scale compresses large differences in intensity into more manageable numbers, making it easier to compare sounds. The formula for calculating sound level in decibels is given here. We have 10 multiplied by the log of I to I naught, where I is the intensity of the sound, and I naught is the reference intensity, typically the threshold of hearing, which is approximately 10 to the negative 12 watts per meter squared. If the intensity of a sound changes, however, we can calculate the new sound level using this equation right here. Here we have beta F, which is the final sound level. It's equal to beta I, which is the initial sound level, plus 10 multiplied by the log of this ratio, IF divided by II. This is the ratio of the final intensity to the initial intensity. And this equation allows us to quantify changes in loudness, such as when we're moving closer to or moving further away from a sound source. The decibel scale helps us understand how different sounds compare in terms of intensity. So for instance, a whisper is approximately 20 decibels, while normal conversation is around 60 decibels. Louder sounds like a jet takeoff at close range can reach about 140 decibels, which is near the threshold of pain for the human ear. Then at the extreme end, sound levels above 160 decibels, these can actually cause instant damage, and it can perforate the eardrum. This log approach to measuring sound intensity really helps highlight just how sensitive human hearing is. Small changes in decibels represent large changes in intensity, and understanding how intensity relates to amplitude and distance allows us to better grasp why some sounds are perceived as louder than others, and why protecting our ears from prolonged exposure to high intensity sounds is super essential. With that, let's jump into a practice problem. This problem says a detector with a surface area of 1 square meter is placed 1 meter from a blender. It measures the average power of the blender's sound as being 10 to the negative 3 watts. Find the intensity and sound level of the blender and the ratio of the intensities of the blender and a jet engine. To start, we're going to calculate the sound intensity for the blender. Intensity is defined as the power per area. We're given both of these values, so we can go ahead and plug them in. Power is 10 to the negative 3 watts, and our area is 1 meter squared. This is an easy calculation because we're just dividing by 1. So our intensity is 10 to the negative 3 watts per meter squared. Now we can calculate the sound level in decibels for the blender. This is equal to 10 log I divided by I naught. I is the intensity of the sound here for the blender. This is equal to 10 to the negative 3 watts per meter squared. And I naught is the reference intensity, typically the threshold of hearing, which we said earlier is equal to 10 to the negative 12 watts per meter squared. Plugging this in, we get 10 log 10 to the negative 3 watts per meter squared divided by 10 to the negative 12 watts per meter squared. Here, our units cancel out, and what we're left with is 10 to the negative 3 divided by 10 to the negative 12. This is just 10 to the negative 3 minus negative 12. This gives us 10 to the power 9. Rewriting this, we have 10 log of 10 to the 9. Now, by default, log is log base 10. So here, what we're really solving when we're calculating this is 10 raised to what power is equal to the value we have in the parentheses, which is 10 to the power 9. This is a really easy calculation. X just has to be 9. So log of 10 to the power 9 is equal to just 9. And now we're left with 10 multiplied by 9. This is equal to 90. The sound level in decibels for the blender is 90 decibels. Now we can calculate the ratio of intensities between the jet engine and the blender. This is going to be equal to the sound level of the jet, and that's equal to the sound level of the blender plus 10 log of the ratio of intensities, the ratio of the jet's intensity to the blender's intensity. And our goal is to solve for this ratio right here. What do we know? We know that the sound level for the jet is 150 decibels. That's the value we were given in the problem. The sound level for the blender we just calculated to be 90 decibels plus 10 log of this ratio, I jet to I blender. To begin to isolate this ratio, the first thing we're going to do is we're going to subtract 90 decibels from both sides. This gives us 60 decibels is equal to 10 log I jet divided by I blender. Now we can divide both sides by 10, and this gives us that 6 is equal to log of I jet to I blender. So again, this is the logarithm of the ratio of the jet's intensity, the jet engine's intensity, to the blender's intensity. To isolate that ratio here at the end, what we need to do is get rid of this log term. To get rid of a logarithm with base 10, you raise 10 to the power of whatever is on the other side of the equation. So 10 to the power 6 is now equal to our ratio of I jet to I blender. 10 to the power 6, this is just equal to 1 million. So what this says is that the jet engine sound is 1 million times more intense than the blender's sound. And there we have it. We've solved this problem. Now we can move into discussing attenuation. Sound waves, like all waves, do not maintain their original intensity indefinitely as they travel through a medium. This gradual loss of intensity is known as attenuation, which occurs due to the damping effects caused by non-conservative forces like friction, air resistance, and viscous drag. As a result of these forces, the wave's amplitude, intensity, and perceived loudness diminishes over time. The thing to note, though, is that attenuation affects only the energy and the amplitude of the wave. It doesn't alter the wave's frequency. Since frequency determines pitch, the sound may be quieter, but its pitch remains unchanged. In addition to attenuation, sound waves can also exhibit periodic variations in volume due to the interference effect. When two sound waves with slightly different frequencies interfere, they produce a phenomenon called beats. This is a periodic fluctuation in loudness. The frequency of these beats, known as the beat frequency, can be calculated using the following equation. Here, F1 and F2 are the frequencies of the two interfering waves. The beat frequency reflects how often the volume rises and falls per second as the two waves move in and out of phase with each other. This effect is commonly heard when two musical instruments are slightly out of tune, resulting in a periodic pulsing sound as the sound waves interfere constructively and destructively. Let's go ahead now and revisit standing waves to understand how they form and behave under specific conditions. As a reminder, a standing wave is a special type of wave that oscillates in time but doesn't travel through space, so the wave's amplitude pattern stays fixed. Objects that support standing waves, like strings, have boundaries at both ends. These boundaries determine how the wave forms along the object. There are two types of boundaries: closed boundaries and open boundaries. A closed boundary does not allow oscillation, and it corresponds to a node, which is a point of zero displacement. An open boundary allows maximum oscillation, and it corresponds to an antinode, a point where the wave's amplitude reaches its maximum. To explore standing waves in more detail, let's go ahead and consider a string fixed at both ends. And in this case, both ends of the string are closed boundaries, meaning they must be nodes. The wavelength of a standing wave, it depends on the length of the string and the number of half wavelengths that fit along it. The relationship between the wavelength and the length is given by this equation right here. The wavelength is equal to 2L, where L is the length of the string, divided by N, where N is a positive integer called the harmonic number. The harmonic number tells us how many half wavelengths fit along the string. Now, I'm going to explain this, and then I'm going to show you a diagram that will help all of that make better sense. So bear with me. Each harmonic represents a specific mode of vibration. The first harmonic, also known as the fundamental frequency, corresponds to the longest wavelength that can fit on the string, producing the lowest frequency. Higher harmonics, such as the second and third harmonics, they correspond to shorter wavelengths and higher frequencies. The frequency of each harmonic can be calculated using this equation right here. This equation says that the frequency of each harmonic is equal to n, the harmonic number, multiplied by v, the speed of the wave along the string, divided by 2L, where L is the length of the string. Now, to make sense of both of these equations and harmonics, let's go ahead and look at this diagram. This diagram illustrates the different harmonic patterns. In the first harmonic, n is equal to 1, so lambda is equal to 2L. The wave consists of half a wavelength with nodes at each ends and a single antinode in the middle. In the second harmonic, n is equal to 2. There are two half wavelengths, meaning that there are nodes at both ends, and there is one additional node in the center. The third harmonic, n is equal to 3, and it shows 3 half wavelengths along the string. All right, we have 3 half wavelengths that are fitting along the string with nodes at both ends, and then additional nodes between the antinodes. These harmonic patterns help explain a lot of things, including how musical instruments produce different pitches. Each harmonic corresponds to a distinct tone, and the combination of these harmonics gives instruments their characteristic sounds. With that, let's move on to discussing open pipes. This is another system that supports standing waves. Unlike strings, which are fixed at both ends, open pipes have both ends open to the environment. This allows maximum oscillation at each end, meaning that both ends act as antinodes where the amplitude of the wave is at its highest. Just like with strings, however, there's a similar relationship between wavelength, length of the pipe, and harmonics. And we see that in this equation right here, where lambda, wavelength, is equal to 2L. L is the length of the pipe divided by n, where n is the harmonic number, and it represents how many half wavelengths fit within the length of the pipe. Now, if we scroll here, we can take a look at the first, second, and third harmonic. In the first harmonic, n is equal to 1, and we have that the length of the pipe is equal to lambda divided by 2. This means that half of a wavelength fits within the length of the pipe. At both ends of the pipe, there are antinodes, and in the center, there is one node. In the second harmonic, n is equal to 2, and the length of the pipe is equal to lambda. So here, the length of the pipe fits one wavelength. We notice that at the ends, there are antinodes, and then there's another antinode in the center. And then there are 2 nodes for the second harmonic. In the third harmonic, we have n is equal to 3, and we can write that the length of the pipe is equal to 3 lambda divided by 2, so we can fit 1.5 wavelengths within the pipe, and we notice we have antinodes in the end, and then other antinodes that appear here, and then there is a total of 3 nodes. With that, let's finally explore our last scenario, which is closed pipes. Now, this introduces a really interesting variation on standing wave behavior. In a closed pipe, one end is closed, corresponding to a node where displacement is 0, and the other end is open, corresponding to an antinode where displacement is maximized. This arrangement affects how the harmonics are formed inside the pipe, and only certain standing wave patterns are allowed as a consequence. In contrast to open pipes, closed pipes support only odd harmonics. Now, the relationship between the wavelength, the length of the pipe, and the harmonic is shown in this equation, where lambda, the wavelength, is equal to 4L, and L is the length of the pipe, divided by n, where n is an odd integer representing the harmonic number. So for a closed pipe, we're going to be looking at the first harmonic, the third harmonic, and the fifth harmonic. In the first harmonic, this is known as the fundamental frequency. The length of the pipe, L, is equal to 1/4 of the wavelength. So when n is equal to 1, L is equal to lambda divided by 4. This is the simplest wave pattern with a node at the closed end and an antinode at the open end. For the third harmonic, which is the next possible mode, the length of the pipe corresponds to 3/4 of the wavelength. So when n is equal to 3, L is equal to 3 lambda divided by 4. This wave pattern introduces an additional node. All right, we have this additional node at the end, our typical one, and then there's another one right here. And it introduces an additional antinode. So we have our antinode at the end, and then somewhere else in the pipe right here. Then we have the fifth harmonic. This corresponds to 5/4 of the wavelength. All right, and there's even more nodes and antinodes here. So when n is equal to 5, L is equal to 5 lambda divided by 4. We have our node at the closed end, and we introduce 2 additional nodes as well. And then we have our antinode at the open end, and then 2 other additional antinodes as well. With that, we've covered strings, open pipes, and closed pipes. Before we end this lecture, I just want to talk a little bit about ultrasounds. So in addition to producing music and shaping everyday sounds, sound waves have valuable applications in medical imaging through a technique known as an ultrasound. Ultrasound takes advantage of high-frequency sound waves that are beyond the range of human hearing to create detailed images of internal organs, tissues, and structures within the body. The principle behind ultrasound imaging relies on the fact that sound waves behave differently as they pass through tissue with varying densities. When these high-frequency waves are transmitted into the body using a handheld device called the transducer, they travel through the tissues until they encounter a boundary between 2 different types of tissue. At these boundaries, some of the sound waves are reflected back to the transducer, while the rest continue to travel further into the body. By analyzing the time it takes for the reflected waves to return and how much of the wave is reflected, the ultrasound machine constructs a real-time image of the internal structures. And this non-invasive imaging technique is commonly used to visualize organs, monitor fetal development, and detect abnormalities or pathologies. Ultrasound, in short, is a powerful example of how sound waves extend beyond simple acoustics, and it offers practical applications in medicine. And with that, we've completed our lecture on waves and sound. I really hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.